Dean of Engineering, Professor Chan, heads of departments, distinguished guests, ladies and gentlemen. A good evening to you all and welcome to the second lecture in the NUS Engineering Lecture Series. And this evening's talk will be delivered by Professor Phoon on the topic, Moving the Earth. Now, before I introduce the speaker, let me say a few words about the NUS Engineering Lecture Series. I'm Professor Chua from the Department of Electrical and Computer Engineering, and I'm the chair for this evening's event. Now, you may have already known that the Faculty of Engineering, NUS, is ranked number 19 in the World University Ranking review by the this Higher Times Education. We are placed better in number 9 in the QS World Ranking University. Now, as highly ranked as we are, you find that the community here are not aware of the good research that we have conducted. And this NUS Engineering Lecture Series is initiated to share some of the significant results that we have conducted, that we have achieved, and research that's been conducted in the faculty here that will continue to earn us respect as a world-ranked university. Now, this series of lectures is also organized to celebrate the peaks of excellence and also the thought leadership. Now, as the name suggests here, series, a number of other lectures are being planned. Each lecture will be delivered by an academic staff from the faculty who has made significant research contribution. And we will also highlight, these lectures will also highlight some of the sea change developments in engineering that will affect the lives in the coming years. Now, I would like to acknowledge the contributions from my committee members who have helped me to put this series together. And they are Professor Arun, who is here. We have also Professor Ang Beng Hua, Professor John Wang, and also Colin Shepard, and we have another one, Professor Ben Chen. Now, I would like to acknowledge the sponsorship from from the companies Penta Ocean Construction Limited, and also POA Corporation for their generous gifts, which has made this event, this evening's event, possible. Okay, now let me introduce the speaker, and Professor Phoon. He's Provost Chair, Professor in the Department of Civil and Environmental Engineering, National University of Singapore. His research interests broadly lie in geotechnical engineering. He was conferred the Norman Medal in 2005, which is the highest and most prestigious technical paper award bestowed by the American Society of Civil Engineers. He was the recipient of the NUS Outstanding Researcher Award and the NUS Annual Teaching Excellence Award in 2010. He was appointed the Guanghua Chair Professor by Tongji University, China in 2010. He is the Editor-in-Chief of GeoRisk and has served as a scientific advisor to the International Center for Geohazards, a board member of the Civil Engineering Risk and Reliability Association, board member of the International Association for Computer Methods and Advances in Geomechanics, strategic advisory board member, Taiwan Building Technology Center, National Taiwan University of Science and Technology, and Scientific Council member to the Inter-Polytechnic Doctoral School in Italy. He's a professional engineer in Singapore, past president of the Geotechnical Society of Singapore, fellow of the Institution of Engineers Singapore, and fellow of the American Society of Civil Engineers. Let's welcome Professor Phoon.
Thank you, Prof. Chua, for your most generous introduction. Good evening, Professor Chan, Dean of Engineering, Professor Lui, Mr. Ong, and many distinguished guests here. First of all, let me thank all of you for appearing this evening at these very late hours. I do appreciate that you took time off to attend this event. And secondly, I would like to thank Professor Chua and his committee for granting me this honor to deliver this lecture. He actually wrote to me, Prof. Chua wrote to me last year while I was enjoying my sabbatical overseas. And I must honestly admit that my first impression was to decline. Researchers are like little squirrels. I like to tell a lot of my friends, we just go around collecting little walnuts here and there, and we are very interested in our walnuts. I'm not sure what the rest of the world think. And we're always busy in our little hole. Sometimes if we are lucky, we collect something that's really nice, and maybe we do something that is positive for the rest of the world, but we don't really like to get out of our hole. And I wanted to say no, but then I quickly thought about Prof. Chan. Actually, Prof. Chan was my senior colleague in the Department of Civil Engineering. And immediately I can imagine Prof. Chan in my head saying, he will give me this very patient counsel and says, Kok Kwang, you need to get out of your little hole and you need to start mingling with the normal human community. And okay, since I'm, all professors are very smart, I jumped to the end point and I decided I'll accept Prof. Chua's most gracious invitation. I'm here today to talk about geotechnical engineering. I really wanted to talk about this topic because I think short of my colleagues in civil engineering, nobody really knows what is a geotechnical engineer. And that, by the way, includes my wife, and my wife is in the audience. There was one time she asked me, what exactly do you do for a living? So I wanted to tell all the things that we do, about all these excavations and all these very nice things that we do. But then, in the end, I decided I'll just tell her, actually, I think people see me as an expert in soils. So she looked at me and said, oh, you're like some kind of high-class farmer or something. Okay, this is a very interesting question because, farmers are interested in that part of the earth, maybe a few meters from the ground surface. And if you talk to a farmer would, wax lyrical about, the soil is like really very, very black, very, very fertile. It smells great, and it's going to be very fertile and grow all kinds of wonderful plants. The interesting thing is that geotechnical engineering are absolutely not interested in that wonderful stuff. We're only interested in that level, say a few meters below the ground surface, maybe all the way to few hundred meters into the ground surface. And our version of what is known as nice soil is to go and grab some soil and say, wow, it feels so strong, so stiff. And so you get something interesting about research. Research is so specialized that the entire planet is actually drawn into layers, and each of us belong to that little layer of specialization. And you get the meaning behind the word that one man's meat is the other man's poison. So we are actually interested in that part of the ground that as I've said, that doesn't even go very deep, by the way, because the mining engineers go deeper than us, and the geophysicists are right interested in the center of the planet. So there's a zonation involved here. And well, we deal with underground space, by the way. That's one of the things that we do. We dig really big holes, and sometimes we also do things that are above ground, but mostly a lot of our activities are under the ground. And among professors, our not so funny joke is that we bury our mistakes because no one can see what we are doing. So I thought very hard about geotechnical engineering, and the only thing I could think about was land reclamation, essentially, because this is something visible to everybody. It's above ground, and and it's something that I had the fortune to be involved in for the past 10 years. So, and certainly, research of this nature nowadays, this is all done in a big team. All right, so I'm just speaking, hopefully correctly, on behalf of many people who are involved in this project. Let me get into my presentation proper. As I said, research are done in a big team now. In fact, one of my closest partners is Professor Tan Tiam Soon. I think he's not here, right, Tiam Soon? He decided to skip out of town. Prof. Tan is probably more of an expert in this area than I. He has been involved in land reclamation for ages, and there are teams of people who were involved in the past, and I hope I didn't miss out any name. And we have an excellent, I thought this is something that was really gratifying, and we have an excellent relationship with Housing Development Board, Sabana International Consultants, and Tua Yen Dino. We've been having this collaboration for easily more than 10 years. So I think this is something that's really nice, I think, for people who are willing to work with us. And of course, I should as Prof. Chua has gratefully acknowledged, we have a Mr. Surumi-san from Penta Ocean, who are sponsor. And we also have a Kamata-san and Mitani-san from Tua Corporation. They are sitting right in front. And of course, they are like very good friends of mine. And that's why they are sponsoring me. But I'm not sure whether they will be my friend after this event, but well, at least they sponsor. I'm going to lead you through a interesting set of projects and methodologies that we do actually in Singapore. As I've said, some of this work were done in the past, and all these things will be made clear to you as I go along. But first, let me show you something that is my favorite. This is not updated pictures, by the way, but I show this picture this is my introduction slides in any presentation that I make overseas. And the thing I like to tell all my friends overseas is that, Singapore is really somewhat of an artificial island because, you see straight edges everywhere, and these are clearly signs of presence of man. You're actually doing something that is visible right from a level of a satellite. And this is the scale of the work, which is the key theme of my presentation this evening, actually. The scale of the events or the scale of the projects that we work on is to me, quite humongous. And I would like to tell him that we reside on this little island. And although we have almost nothing, but we are very resourceful. Someone who has no resources are very resourceful. That's the irony of the whole thing. And the other thing I like to claim among my colleagues overseas, they all belong to a very large country. I cannot beat them in the, which country is bigger kind of thing. So I just tell them that I'm older than my country. They can't win me on that one, for sure. It is true, by the way, it's factual. A lot of us are older than our country. Some of you may not be quite aware that actually Singapore started with I'm just tracking the statistics from 1960. And we start out with an island of an area of about 580 kilometers square. And this is entirely man-made, by the way. Over the past 50-odd years, the size of the island went up by 20%. I think this is a record for independent nations. I'm not sure whether there's any country that can grow at that rate. This is like the growth rate of a baby, right? But it is, to me, pretty amazing when I look at the statistics. And I took this, by the way, I took this from Straits Times. Again, these are dated information, but it's illustrative enough to show you that this yellow part represents our original island. This is natural. And the brown and the orange are all man-made. So, and some of these are known to all of you, our very famous Changi Airport, Jurong Island, Tuas. These are major reclamation projects, but we also have others, by the way. Some of them have been completed, some of them are ongoing. By the way, this is just a good reference point. If you look at the unit of hectare is the unit of area. So you can imagine a hectare to be something like 1.3 a soccer field. This will give you an impression of the numbers that I'll be presenting subsequently. Now, this large-scale coastal reclamation essentially began, the story began in the 1970s in Singapore. We do have a reclamation prior to 1970s using some of the hill-cut materials in Singapore. But subsequently, immediately, it ran out of hill. That's quite obvious. No more hills for us to cut. And one of the very famous projects at that point in time in the 70s was Changi Airport. Not the current Changi Airport, the original Changi Airport. The whole project took place from 75 to 79 over a period of about 4 odd years. 750 hectares. As I said, do your rough conversion to football fields. You're talking about, these numbers are, as I've said, presented to you to let you know we are talking about to reclaim this piece of land, you need a 40 million meter cube of seabed sand. We actually dredged the sand to reclaim a Changi Airport. And doing some rough arithmetic, you end up with something like 22,000 meter cube of sand per day for this particular area. And also take note of the fact that roughly you need about 5 meter cube for every meter square of land. This gives you an impression of the depth of the sea that you're reclaiming, roughly of that order of magnitude. How much is 22,000 meter cube per day? I thought, volume is not something that people can appreciate. So I just go and take one of the very famous structure and some of you could have visited this Sydney Opera House in Sydney. One of this Sydney Opera House would have a volume of 26,400 meter cube. So that's the volume of this Sydney Opera House. And if you look at the numbers I just cited to you, 22,000 meter cube of sand per day, you're dumping Sydney Opera House into the sea every single day. That is a massive job, by the way. And many, many little things that very, very clever, very, very neat things that we can think about that we want to do, nothing works at that scale. Simply, the scale will simply defeat all your ingenuity. I thought I would run through, since not all of you are working in this area, and this is something that perhaps I could acquaint you with. The whole procedure of reclamation is quite simple. Imagine this is your original sea coast. You wanted to move your land laterally by this amount. The first thing you need to do is to construct a sand quay. That is to retain the field that you will be dropping into this retained portion. And this sand quay is something that I would actually skip to at the end of my lecture. So you want to bear in mind a sand quay is essentially a retaining structure. And the way we do it is very simple. We dig a big trench in the sea. And we replace this trench by sand. The reason is because in order for this structure to be stable, you need to have a solid foundation. So there's like a foundation to ensure the stability of the new shoreline. This is a very interesting picture. You notice that to do this piece of work, you already have to dredge a seabed materials. And when you dredge this seabed material, by the way, you cannot throw it, elsewhere. Singapore is not only very, very small in terms of land area. Singapore has very, very tight navigational channels. The sea are being used for shipping. You cannot go around damaging these lanes. That is obviously not desirable. So the usual trick is to just dump the dredge material into this over a sand blanket, and then you basically rain sand on top of it using some fairly big barges. And when the land rises near to the sea level, you bring in the smaller barges because you don't have enough draft for these barges to enter into these shallow areas. And then subsequently, it becomes so shallow that your small little barges couldn't come in. And you just keep raining sand using a trailer suction hopper dredger. So basically, these are all sand, by the way, hydraulic sand mixed with water. And you're just pumping this sand continuously. So this picture is basically telling you how you dump this Sydney Opera House scale of a sand to reclaim your land. That will give you a good impression, I guess. Now the story gets more interesting because notice that the original Changi Airport was reclaimed in the 70s. And then, of course, this entire construction procedure never stops. We were reclaiming land all over the place. So these are just so-called some of the examples and samples that I'm sharing with you. For example, in Pulau Tekong, we did it in the early 80s, and that requires a 5.5 meter cube per meter square of land. The water starts to get deeper. This is common sense because the seabed has to go deeper, right? As you reclaim outwards, you have to go into deeper and deeper water. In fact, by the early 90s, that is just roughly 10 years ago, in Changi East, this is the new extension, you are already dealing with a 13 meter cube per meter square of land. So you can see the trend. The trend shows that it's getting more and more difficult because to reclaim that single extra meter square of sand, you end up having to dump in a lot more sand. Now you're at a volume of 272 million meter cube of sand. So if you add another zero, you'll be in the giga scale. This is no longer mega scale, but giga scale magnitude. And then this is very difficult. As I've said, this may be a cleaner picture, but the way I took it from MND. Again, it shows the, very visually, it shows you how fast we are growing and all the new pieces of land we are creating. That is very impressive, 20% as I've said just now. But the population of Singapore has also been increasing, as all of you know. We started off with something like 1.8 million people, 1960s. And currently at this stage, there are like 5 million inhabitants on this island. So this is the rate of growth. If you take the extra piece of land, you divide by this X number of people, you will just end up showing that despite this tremendous growth in the 20% growth in the size of our land area, we are indeed getting denser. This is population density. Just simply taking your population, divide by the land area of your island. And as I've said, this is a 1.8 million, 1960, and then this is 5 million. If you just divide the land area, the population density went up by 170%. So we are getting denser faster than we can grow the land. The statistics are very clear. You all have heard about this economic strategies committee and the recommendation, but I'd just like to highlight the one of the key, I wouldn't say key, but there's a very interesting subcommittee on maximizing so-called value from land as a scarce resource. I cited this paragraph because it is relevant to my presentation. And one of the important heading here is that the government intends to invest ahead to create land and space. And they do recognize, the government of Singapore do recognize that land is a strategic resource for future growth. I think that is very obvious. Without land, you cannot initiate any activities. Residential, economic, everything needs land. I mean, unless we learn how to float on air, you need land. There's no doubt about it. And the recommendation is that the government should take the lead to create this space. And to create this space, that will include intensifying land upwards. I suppose that involves building taller structures. Downwards, that will involve digging holes in the ground. As I've said, our holes are getting bigger and bigger, no doubt. And I think it is quite clear that we need to reclaim land as well. So the challenge is there. This is just a strategy. And how to go about implementing this strategy is really interesting. I hope to show you some of our tentative solutions this evening. I don't think we are, as you can see, reclaiming land has been taken place in the past, is being done now, and certainly it will continue in the future. So we are just the current players, so-called. You will not end with us, nowhere near to it. But just to recap what I just discussed just now, we inevitably our reclamation depth is increasing. We're also running out of nearby sources of sand. So we don't have this kind of a luxury of using sand as a fuel. And also there's increasing, even before the Economic Strategies Committee report, we are already exploiting underground space at a more and more intense level. So just to, this is a very famous project, the deep tunnel sewage system. By doing that, you actually free up 290 hectares of land on the ground surface. So this is very, very clever, right? You actually open up existing land space by moving facilities below the ground, but you generate a 6 million meter cube of soils in the excavation, and that has to go somewhere. And there's really no place for you to go actually in Singapore because we are very, very tight, in terms of land use. And actually, some of you may know that the last landfill site in Singapore has closed in 1998. So there's a lot of our waste now is incinerated and is being dumped into Pulau Semakau, which is another reclamation project, by the way. So I hope I've convinced you, just running through this very brief short outline of what has happened in the past, that the volume of fuel needed for any reclamation work is really, really humongous. And when we talk about, for example, this Changi East project again, I said it's about 200 million cubic meter of fuel. It will require you to dump a 2 Sydney Opera House continuously for 14 years. This is the scale. So the question that we must ask ourselves, there's no doubt about it, is where do you get this mega size field? We don't have hills to cut anymore, as I've said. And I could offer 3 options for discussion this evening. One, of course, obvious procedure is that maybe you want to bring sand further from further afield. And I'm going to use this number, 272 million meter cube of sand as a back of the envelope calculation, just to look at what these numbers translate to. If you're going to ship this amount from elsewhere, you pretend that we use our barges, and I'm using numbers that like 5,000 meter cube barges. These are somewhat big barges that we're using nowadays. If you do this over 10 years, this amount of fuel would take 10,000 barge trips per year, because you need the barge to move to and fro your reclamation site. Now, the Port of Singapore handles at the annual level 140,000 vessels per year. That means that you're taking up a big bandwidth of this vessel traffic if you wish to move this amount of fuel. I thought I'll bring in another interesting bit of historical tidbits here. You all may have heard about Operation Overlord. There's a very, very interesting operation. We call it D-Day, Normandy, the Normandy invasion. And the D-Day Armada, by the way, consists of 7,000 vessels. Of course, the tonnage of the vessels are very large, but I just wanted to highlight to you, just pure numerical terms, the whole D-Day Armada is 7,000 vessels. You will be assembling a D-Day Armada every year to bring all this, and this is like in the past, this is a past reclamation project. So you're talking a lot of barges just to achieve this particular goal. Now, the second option is for us to give up using sandy materials. And for something that big, by the way, the kind of scale that we're operating in, you need to think about natural fuel. And the only natural fuel that you can actually use at that scale is clay. So besides sand, you have to do clay. Actually, there's no option at that kind of scale. I'll talk about this later. In fact, a lot of our recent work has been done looking at how we can manage this material. This material, unfortunately, is not that great. You cannot use it like sand, just dump it with no treatment. I'll explain later. The third option, by the way, is to use your unwanted soil. Again, this is very, very clever. By the way, I think, if I'm not wrong, Prof. Tan, and I think Prof. Liu has written papers on this. We have all this huge amount of unwanted fields that you will be generating more and more of this if you wish to dig holes from the ground. Right. So if you're going to do more MRT tunnels, if you're going to build this science city below Science Park, then this volume of fuel occupied by this hole has to go somewhere. Wouldn't it be really interesting if that kind of material, you just take it and dump it, and then you get a new, so you're like getting two economic benefits for one action. But of course, unwanted soil is something that is tricky, simply because it's random. You're taking it from many, many different sources. It is not the same as your natural fuel, that is for sure. And you need to engineer it. This is actually a very intriguing, to me, option. We are still working on it, by the way. Not so easy, but the concept by itself is very intriguing. I'm going to go through for the next perhaps 15 minutes or so, I would like to go through some of these variations that we have studied. And some of these, as I said, are done by my predecessor. In fact, the first scheme I would like to discuss is the use of clay slurries. Clay slurry is just our technical term for muddy water, So there are a lot of water, there are very little soil. But before I do that, let me at least, since this is a general audience, I will need to share with you, as far as reclamation purposes are concerned, what exactly is this difference between sand and clay? I show you this very, very simple picture to show you that this is sand, this is clay. The primary difference in this case is size. And what kind of size differences are we talking about here? We classify anything, these are taken from our international standards. And the key thing I would like to highlight is that when you talk about sand, the boundary is about 0.2 millimeters. This represents roughly the diameter of a fine sand. If you're talking about clay, you're talking about 2 orders of magnitude lower. So internationally, we define clay-sized particles to be something like 2 micron. That's 2 times 10 to the power minus 6 meters, or 0.002 millimeter. Just to make sure that we are connected to that number, by the way, the diameter of a human hair will be in between these 2 numbers. So you'll be 0.02 millimeter. That will be the diameter of your human hair. Very, very fine particles compared to sand. And I'll show it to you another way. This is a 10 millimeter scale sand, very beautiful sand from Gobi Desert. You notice that sand has a shape that is, somewhat spherical. And as I've said, the dimension of the sand, the diameter of the sand is of the order of about 1 millimeter or less. This is a scanning electron microscope of our clay fabric at Pulau Tekong. So this is our Singapore clay, by the way. You want to know how it looks like? It looks like this closed up. If you look at it with your human eye, it's just one, gray mass of thingy that you can't tell the difference. But actually, there's a structure in it. And this is a typical structure of clay, very flaky. They all look like plates, and they occur at very, very small scale. By the way, this is a 10 micron. Now, what this implies is this, as far as reclamation work is concerned, it implies that the spaces between the sand particles are much, much larger than the spaces between the clay particles. That is the observation that we need to draw here. Now let me explain how this phenomenon is related to what we are really interested in. When you're interested to use whether sand or clay as a reclamation field, all this field will come with water. So this could be your, whatever are your field materials. And because you're working right in the sea, they must be full of water, right? Now, the job here is to somehow think of a way to compress this material and drive the water out. You can't use the material as it is. All right, so this is just a cartoon to show you that essentially you want to achieve this a dense state, you need to do this. Now in the case of sand, this is not a big problem. A simple analog that I would draw here to show you how this phenomenon works is to pretend this entire mechanism is like a piston with a hole. So it's a leaky piston. The water is here, there's water in the piston, and then there's a spring. The spring represents your field. So the idea here is that you want to apply a load, and hopefully you can squeeze the water out, and then the spring get compressed. So this is a very simple model for you to visualize. And of course, in the case of sand, remember the size of the sand is of an order of 1 millimeter. The holes are also roughly of that order, 1 millimeter. Clearly, if you were to conduct this experiment, you will find that the water will flow out very freely. There will be no pressure detected usually within your field. So this is a very, very good field material. Hence, traditionally, all around the world, we try to use this so-called sandy material for this very simple reason. Now, in the case of clay, if you were to do this, maybe I got through a little bit fast. In the case of clay, if you were to apply it, you'll notice that the hole here is very, very small. This entire process would also happen. In other words, you can gradually squeeze the water out of this little void space. But the entire procedure is very, very slow. It's not slow as far as Mother Nature is concerned. I hope you understand that Mother Nature works on a geologic scale. Geologic scale, you're talking about something of the order of millions of years. And having this activity taking place over millions of years is more than sufficient for nice things to happen. But the other constraint, all right, so that brings in the second constraint. The first constraint was huge amount of field. The second constraint is time. No reclamation project will take 1 million years to execute. That is for sure. No one is going to pay you to get the job done for 1 million years. So we cannot do it by geology. You want to do it fast, you got to think of a way of getting the water out as quickly as possible. That's where geotechnical engineering comes in. By the way, there's even more interesting analog that I always thought about, whenever I'm watching a cinema. When you go and watch a movie, there's always an advertisement telling you what to do when there's a fire in the cinema. Then they'll say, everybody run to the exit and you must queue up to get yourself out. Actually, the whole procedure is like consolidation. If there's only a little hole there, man size, and all of us try to get out now, we'll be like knocking into each other, and only one person can go at one time. No doubt, takes lots of time. If I open the entire panel of doors, everybody gets out quickly. So this entire consolidation is no magic. You think about that when you're watching a movie. Don't ask me why I think about all these things, but I already told you researchers are obsessive. I can't defend on that point. And sometimes we're also a bit too insane, but we do get nice things done. I wanted to talk about this very clever idea, so-called the clay sand sandwich scheme. And the inventor of this scheme is Professor Lee. He's sitting in the audience, Prof. Lee. I got to say something about Prof. Lee. Prof. Lee was the one who brought me into NUS. So I have him to thank for, I hope, Prof. Lee. You got me into this job. And Prof. Lee invented this scheme, 1987. He thought about this clever idea that you have all this muddy water. These are things that you need to get rid of, but you cannot get rid of muddy water, I told you. You need to consolidate this material. So his key idea, let's pretend the blue part is your muddy water, slurry. A lot of water in there, very little soil solid. Prof. Lee thought about this clever idea. Why don't we put a thin sand cap on top of the slurry? So you add a little bit of sand. You're not using up your sand like the way we dump sand, just now, Now you're using some clay, you're using a little bit of sand. And because this thing is so watery, just that little bit of sand, the weight of the sand would actually cause the clay to consolidate very, very quickly. So water would just flow up, and a sand layer would act as a drainage layer to get rid of water. It's also acting as a weight to compress, very clever. To accelerate the consolidation, and you just repeat the entire procedure. And you build it layer by layer. By the way, Prof. Lee, I saw this thing being executed in Busan Port. They use the same procedure. We tried to tell them that we have done it, but they did not quite acknowledge it. So sometimes you get a bit upset when you see your colleague's clever idea being adopted, and then they said that they invented it. The only thing they invented that was very smart, Prof. Lee, was that they used bamboo mats to actually drain the clay. By the way, all these things are happening at a port because at a port you got all this very soft slurry stuff that you need to consolidate into something useful. This project, by the way, and also another person is Prof. Karo, another senior colleague of mine, and he and Prof. Lee are in the same team, and they actually done it, So this is not just storytelling. By the way, there are a lot of stories that we can tell, but the difference between storytelling and doing research is that you get the job done. The devil is always in the details. It's not in the general principle. And they demonstrated that this thing could be done. 40 hectares they did, beautiful piece of land. They showed that this thing can be done just using about 15 centimeters of sand, very little. Of course, they found that the trick is how to get the sand to form a layer. If you put too much sand, you get too greedy and say, why don't I put more sand so that it becomes heavier and I can accelerate faster? Then the sand will go inside your slurry because your slurry is very weak. So you cannot put too much, you cannot put too little. Hence, I said the devil is always in the details. And probably they all came up with a clever idea of spreading this sand using a horizontal pipe so that you don't dump sand like the way you hose a garden. You do that, the sand will just go into the slurry. So they are very clever. They put this horizontal pipe that goes over the field and allows you to spread the sand in a uniform way. Probably, I hope I got your idea correct. Okay, there is a limitation to this procedure, and that is that this procedure requires slurry, soft material. If your source material is not slurry in its original form, let's say you take excavated field onshore, say MRT tunnel projects, deep excavation. I show you this simple picture. By the way, these are all drawn to scale. This represents the typical water content of our natural clay. You can't see the water because the water is mixed with the clay. but I just artificially separate the clay solids and the water. So this represents, using this very simple phase diagram, your ordinary clay. Now you want to convert this clay to a slurry, 200% water content. Slurry has water content higher than this, but I thought I'd use this as a lower bound just for demonstration. You add this much of water there. So this is how much water you have when you're talking about clay slurry. And then you have your clay slurry, you need to remove the water again. Excuse me, you need to remove the water again to get back to your original clay by applying a surcharge. So what you're doing is that you're adding water to turn it to slurry, and then you're removing water to get back your original ground. Clearly, this is something that is, in my opinion, probably not the original intent of this procedure. The procedure has always been to, the starting point has always been slurry and not a original ground. I wanted to talk about a very nice variation. Prof. Lee may have heard about this too. You know, Prof. Lee's method is to put a sand on top of clay. Why not put a clay on top of sand? Just invert the thing. And then put some sand drains. Sand drains is just nothing but vertical column of drains. You got to apply suction at this bottom layer. Water will go into a sand drain. You will get your slurry to compress. Very clever. If you do that, you don't have to care about this sand dropping, penetrating through your clay because it's already at the bottom. So you won't have this problem. That is the advantage of this procedure. The distinct disadvantage of this procedure is that you need to apply suction. Suction means money. Where do you get suction from? Suction doesn't grow on trees. You cannot get suction by sucking, by using your own lungs. It doesn't work. Prof. Lee's method, in my opinion, what is clever about that method, if you can solve that thin layer of sand, is that he relies on gravitational energy, and that's free. You know, using the weight of the sand is free. Gravity is free. Suction is not free. And not easy to maintain suction also. Again, there are a lot of clever technical details here which I will not explain. But I want to tell you that the Japanese have done it. I think Surumi-san may know about this island. It's called Yomishima. Shima means island in Japanese. I went to this site I think about 10 years ago to visit this reclamation site. In Japanese language, or rather in English, this translate, those who can read Chinese can, this is called the Dream Island. Interesting. It's called the Dream Island, but actually it's made of landfill. So I think the name is very innovative. We should have called our landfill Dream Island also. It gives a better PR than saying it's a waste field. And they did it actually as part of their bid for the Olympics, which I think Japan failed to secure. But I think this project is still ongoing. That's what they did using suction to, but this is not reclamation, by the way, this project. This project primary intent is as a waste dump. So what you do is that every time you get excess slurry, you throw in there, they apply suction, they compress, and then they repeat the procedure. But of course, by doing that, eventually, when you top out the entire size of this containment pond, you get a free island. And the Japanese told me that they're going to change it to some kind of golf course, and they're going to build beautiful resort housing on it. So maybe we would go, my wife and I, one day to Yomishima. Remember this, very nice. Now, we talk about clay slurry, but that's provided you have clay slurry. Remember, just now I mentioned something about the fact that eventually we'll deal with all this unwanted material coming from underground sources. These are fairly stiff, by the way. This, I just use a term called clay lumps, by the way. And these clay lumps would appear if you excavate from underground construction. Even if you go to the sea and you start dredging. By the way, the mud is only very soft near to the surface of the seabed. The strength of the clay actually increases with that. It gets stronger and stronger. You can see these are the lumps that we dredge from the sea. They are very stiff. And I put a human body there to show you the kind of scale that we are talking about. And this is the kind of clamshell grabber that was being used to dredge. And you end up with all these boats full of all this lumpy clay. As I've explained, this lumpy clay has a water content of maybe 80% or so. And well, would you really want to take this a stiff clay, mix it with water, make it very soft, and then repeat the entire procedure? It will appear that why don't we think about just dumping this into the sea directly without additional pre-treatment in its original state? And this is done actually, I think it was about 5-6 years ago. There was a site in which we tried taking these clay lumps, and dumping it. Very interesting batch, by the way. We just opened a batch from the bottom, and all these lumps would drop into the reclamation site. But again, there's no, as I told all my students in all my lectures, in this world, there's no free lunch. Any clever idea to think about, Mother Nature will think of an even more clever idea to stop you. I think all the researchers know that. Hence, as a researcher, we need to be very, very patient. And as I said, we need to be insanely optimistic. You deal with lumps, the main problem is that the lumps cannot be arranged in a matrix, like a natural clay, where there's no void. Because the lumps comes in random sizes, random shapes. And if you dump them, you may get a shape like this. And therefore, there are these voids between the lumps. By the way, the voids between the lumps are big, right? Say 1 meter. The voids between the lumps will be of order 1 meter. The voids inside the clay, remember, clay is 2 micron. You're talking about a 6 orders of magnitude, if I'm not wrong. It has little voids in there as well. This is a system where there are 2 voids, a double, what we call a double porosity system. Very, very highly nonlinear system if you're analyzing this, because the voids in here within the clay is a lot smaller than the void between the lumps. These are huge. And of course, the primary concern in this particular project was to take note whether these voids were closed. So very quickly, maybe I'll show you some of our laboratory results. Just to show you what we did. Of course, we're using fairly small scale samples, about 100 millimeters. These are not big scales. And what we did was that we apply load on top of these lumps. And what we noticed is that by the time we reach something like 50 kPa, we managed to, at least visually, we cannot see the presence of interlump voids, but this is only visually. What we decided to do is to do a permeability test. This to see how well the lumps or how well water would be transmitted through the lumps. So if you have voids that are connected, water will flow through very quickly. Water is not very dumb. If there's an open channel, water will flow. Water will not bash its head and try to go through all those little voids. That is like very stupid water. Our water is very clever. So if there are voids and the voids are interconnected, permeability will be very high. If the voids are no longer connected, the permeability will be very low. In fact, permeability will be controlled by the permeability of original clay. So when your lumpy field, which is the red dots, were to converge to your green dots are the natural material, we think we have closed the voids. But I think the problem here is that I use the word connected voids. So we are still not sure whether the voids, there are still voids, but they are not connected. So cannot be detected using a permeability test. So we decided to go bigger. By the way, these are all heartbreaking tasks done by our graduate students, Dr. Kati. I acknowledge him. I'm not sure whether Dr. Kati is here. He's probably not here. We are now using lump sizes of 200 millimeter in a huge tank. And what we do next was that we are monitoring the compression of this lumpy field as we apply load. What is really interesting here, and this doesn't depend on voids being connected, by the way. What we found here was that if your load were to be too low, you have this signature, this blue line signature. You have a rapid drop in your settlement with time. By the way, this is a time scale. If you apply enough load onto your lumpy field, you will end up with a pink line. And the pink line is actually the classical so-called settlement curve with time for clays without voids. So this is the way, another way in which we are trying to argue that perhaps by applying 100 kPa of loads, you can get rid of this so-called inter-lump void problem. Now, this technique, by the way, has been done also, and it is effective. We've actually done it, and we've actually succeeded. This particular picture I show you, let me just quickly rewind. This particular picture that I show you has been done. This is not a schematic. We actually have a reclaimed land using these clay lumps, 8 meters thick. And what we did was that we put another blanket of sand 8 meters thick on top to act as a load to compress this layer of lumpy fill. So we have done that. I'm perhaps running a bit slow. I'll finish up very quickly now. The thing is that you need time. There's no doubt about it. You need time for the clay to swell, for the clay to slowly soften, and then slowly for the void spaces to close. You need that. But the other thing that you need is that you need a lot of sand. You actually need more sand than the previous clay sand scheme that I just mentioned. I told you we're using 15 centimeter layers, but here you're using 8 meters layers to serve as a dead load to compress this clay material. And I already mentioned in my introduction that we don't have that much sand. And the other rather I think significant limitation is that you cannot put this lumpy fill above water level. One of the things that we found was that this lumpy fill needs to be submerged underwater so that the clay lumps could soften, swell, soften, and by doing that, the interlump voids will close a lot faster. So putting it above sea level, that will not happen. Now, this thing about building land above sea level will come into place later. It's going to be quite important. I will talk about that at the end of my presentation. So what we do now, by the way, we are now almost at this current stage where we're at now. We are exploring the use of using slurry. So we are back to square one again, except that our slurry is not, has lower water content than what Prof. Lee has suggested in the past. And we are going to add a little bit of cement. This doesn't sound very innovative, but the thing that we are trying to do now is to use as little cement as possible. Clearly, when you talk about adding cement, if you just add a few grains, you can expect things to magic to happen. That will be very strange. So you need to add a certain minimum amount of cement content. And we are now adding almost on the verge. The cement we're using is almost on the verge of the thing not working. So it's like on the verge of working or not working. We are trying to optimize the use of this cement to see whether we can produce a product that is usable. Now the key feature, we call this a stabilized dredge fill. As I've said, the key feature is that in this particular so-called a proposed solution, we do not need to remove water. That saves a lot of time. The water in this case is being used to react with the cement. So you have back your same figure, soil solids and water. You add a little bit of cement. The magnitudes are given here, very little, compared to the amount of water and clay that you're using. And based on, which I will not describe, based on physical chemical change, you end up with an entire solid cement clay product. And that's your fill. There's no removal of water in this case. What happens is that essentially your cement will react with the water and the cement will react with the clay. It's very interesting. This is a scanning electron microscope picture. I took this from my good friend, Dr. Watabe, from Port Harbor Research Institute in Japan. And this is the kind of clay structures that is being formed. These little needles are basically this particular material called ettringite. Ettringite is something that you see even in concrete when cement hydrates. So it shows that cement is working well with clay. You can form a product that is not separate. Eventually, because of this chemical hydration procedure, you actually form a new material, a new engineered material. Prof. Charles says that I need to show you some big projects around the world and not just talk about Singapore. So, Prof. Charles, I'm doing this slide for you. This particular piece of work has been done in Japan, actually, except that they're using different methods and they're using quite a lot more cement because the dredge clay material around, by the way, this Haneda Airport, forgot to mention. You know, Haneda opened a new airport, international, I think maybe 2 years ago, if I'm not wrong. And now, you can actually fly to Tokyo. Haneda is a Tokyo domestic airport. Now you can actually fly to Tokyo from Singapore through Haneda. You don't have to go through Narita. Narita, you will take, I think, an hour or so to reach Tokyo. The only thing that is very important here, by the way, just to sidetrack a little, the Japanese taught me this. If you're landing at Haneda, by the way, you must make sure when you land, it's during daylight hours, so that the MRT is running, the subway is running. Because if not, the subway is not running, you land there, then you're dead. You know why? Because you cannot afford to take the taxi to the hotel. You better learn this trick. When my Japanese friend told me that, I immediately memorized. You don't want to sleep in the terminal for nothing. The subway system don't connect to the airport operating hours. Anyway, they built this very interesting airport. This is totally artificial. Latest D runway. Very interesting. The airport part of it is land. This is land, by the way, reclaimed land. This part is totally supported on a pier section. So this is not even land. This is just like a bridge, a deck of a bridge. You're like launching planes like on an aircraft carrier. Very interesting technology here. And they have actually used some of this particular material as a fill. The entire parameter of this airport has been filled with this cement-treated material. So I think this is enough to show that the concept works on a real scale. This is the structure that we use in Singapore. I'm not quite allowed to say where we are doing all this because the project is ongoing, but this is to tell you roughly how this material is being done. Essentially, we're using this material to replace the sand key. That was what I told you at the very beginning of this lecture. You need a sand key to retain the new coastline. You need it. And what we're doing now is that we're replacing the entire sand with this what we call SDF material. And just a few quick pictures to show you how this SDF machine works. Essentially, you build all the little dikes, and then you just come in and you start casting. So it's a bit like casting concrete. And finally, you put in your stone revetment, and you have this containment structure. Just a very few pictures, so that I won't take up too much of your time, to show how this thing works and how the casting works on site. Eventually, all these things would surface. When you cast a sufficient number of layers, eventually they will daylight, and you will see them appearing on the surface. What is interesting here is that the production rate is pretty high. You're talking about something like 200 meter cube per hour per vessel. So you'll be roughly like, if you do it continuously, say for 20 hours in a day, you will get 4,000 meter cube. Within 5 days a week, you will get your Sydney Opera House. 4,005, 20,000 meter cube. So this is something that is doable. And so far our experience is that we have cast 3 million meter cube. We have found two very interesting features of this material. I'll share very quickly with you. And one is that because you're casting so much material, and because this is a chemical reaction, you actually generate temperature. The thing becomes hotter. You know, our sea water temperature is perhaps about 28, 30 degrees. What we found when we measure we put in a temperature probe into this material, because of this is a massive material, by the way, you end up with 38 degrees. And this is sustained over 5 months, over the period of measurement. I think the temperature is still ongoing. So the material is gaining strength very quickly, by the way. When you heat a material, this material will just accelerate its rate of strength gain. Now, this is a very important point I'll come to later. The other thing is that I told you this is an engineered material. You know, human intervention involved in creating the field. So the beautiful thing is that we generate results that looks like this, highly, highly scattered. It shows that we need to do something about it. Currently, what we are doing is that we want to make sure that the minimum value achieve our design target. But you can see that there's a lot of room for improvement here. By the way, this scatter is not because we are doing the job poorly in Singapore. I took the same set of data from this Haneda airport, Dr. Watabe, same scatter in Japan. So this is an inevitable outcome of our using engineered field. How do we go about treating this is interesting. It's actually something being studied because this is not homogeneous. Clearly, this scatter will affect your engineering design. And we need to perhaps think of new engineering design approach as well. In fact, one of the things we're working on now, just to draw a schematic, as I've said, we use this so-called elevated temperature as a technique to think about whether we can use it as an early quality control device. We need to have quality control because you have scatter, number one, I've already said. And secondly, on the actual site, the temperature of the material is also high. I just show you a very simple schematic. This is the strength of the material versus curing days, log scale. This represents a typical strength gain profile. Typically in design, we design for this particular dot, which is at 28 days. Now, this is what we do in the concrete industry. Of course, the big thing that will occur to you immediately, is that if on 28th day you found that this material is not so great, what are you going to do? There's a huge amount involved. Are you going to excavate out the material? That thought should not be in your head. It's quite scary, actually. We can't actually do a test to verify the strength that we are designing for. We can't do it the usual using this kind of simple, what we call the unconfined compression test. Our limit is about 3 to 7 days. So 3 to 7 days, we can get an indication using this particular test. But 3 to 7 days is still a long time. So now what we do is that we are trying to see whether we can gain an indication, early indication of strength, 1 day or less. We are pushing it to see how we can, and our idea is very simple idea, and it works very well, by the way. We cook the sample. So now we are into cooking now. We take the sample, we cook it, heat it to 60 degrees, and now we are doing higher temperature. And remember, if you cook the specimen, you can get a strength to gain very quickly. So perhaps within a day, you will gain some strength that you can measure, of course. And you see whether you can find a relationship between your desired target and this early strength. This has been done, and actually we found that it works, surprisingly. Of course, the original thought is that you cook the thing, will you go and, will you crack the thing? Will you induce thermal stresses and damage the specimen? So that the specimen, the cooked specimen, has nothing to do with the original specimen. It's like cooking egg, right? Hard-boiled egg and raw egg, not the same. So that was our worry. But as I've said, we actually we demonstrated, this just to show, I think this is the only technical slides I have. This shows you that this is your normal day so-called uncooked specimen. This shows you the accelerated specimen. And also we tried using interesting measures of the stiffness of the specimen. We found that there's a very nice relationship, very, very surprising. And we are able to get a clear-cut estimation of your 7-day, 28-day strength before 7 or 28 day. So if anything happened, I think we got a chance. At that point in time, the specimen at the actual site is still very low strength. You can now contemplate taking out defective so-called material without having nightmares or turning your hair white. So I think I better stop here because I run out of time now. I wanted to have one final slide to talk about the kind of thinking that we're having now. As we work on this, we keep finding new problems. We keep finding new solutions. As I've said, there's no end in research, by the way. We are always trying to take an incremental step in the next envelope. And you can see that, basically Prof. Lee passed the torch to us. We have to pass the torch to another younger group of researchers. We are now talking about creating space above ground. This is called reclamation. As I've said, Prof. Tan, they have been contemplating whether we can use unwanted soil. You are creating space underground, you generate unwanted soil. That's another challenge. You do not know what to dump, what to do with it. And recently I was involved in this climate change project with the NEA. Prof. Leong and now one of my colleagues from TMSI was the PI for this project. And we are now worried about climate change, sea level rise. So, well, I'm not an expert in sea level rise, but if sea level rise were to be true, you're no longer talking about just simply a matter of creating space. You may have to think seriously about protecting your space, which is what the Netherlands are doing, right? They build all these dikes to protect their land. Because if you have to get all this incursion, you have no land. The sea will reclaim you. You don't reclaim the sea is coming back at you now. That is scary. Technically, this is higher order of magnitude now in terms of engineering. Why? If one of these days we need to protect ourselves against the sea, your sea level is higher than the land. The risk is, you cannot, the risk is not the same as your land higher than the sea, obviously. This is not something that you can think that is the same. We do the same design. We do the simple factor of safety. You can't think like that. Because if the thing breach, what do you get? You get Hurricane Katrina. And that, by the way, is something that is earth-shaking. You have changed the entire design philosophy in the US Army Corps of Engineers. They're involved in all this levee design. And for the past few years, since I've been attending their conferences, the US Army Corps of Engineers has been subjected to tremendous pressure. They used to say that the levees are there to protect people, and now they have totally changed their philosophy because I think it is not a tenable philosophy. So now they talk about risk reduction. That's about as far as what engineers could do. Risk reduction. We do a good job, but you cannot reduce the residual risk to zero. Hardly possible. If you do that, then there's no engineering, in my opinion. So we are now struggling between these three things. If we can do something to these three things together, I think we are contributing to nation building in our faculty, among our colleagues here. Those who are involved, we could potentially do something that will be useful for prosperity. I think I'll stop here, Prof. Chow. Thank you very much.
Now, one take-home message I have from attending this Prof. Phoon's lecture is that in geotechnical engineering, you're trying to compress geologic time to human times.
That's right. Very true.
Okay, now I think we have time to take a few questions from the floor. It's open now. Now maybe to kickstart this session here, how long does it take before the sort of soil is settled enough for you to build skyscrapers?
I think typically, if you look at the length scale of this reclamation project, I mean, some of these particular projects may take a while longer. I think the marina reclamation took a while longer. But typically, when you finish reclaiming the land must be usable. That's the specs. That means the land is not supposed to compress by an amount that cannot be tolerated by the usual buildings. So the reclaimed land is supposed to behave almost like a natural piece of land on delivery, which means that the scale is maybe 5 years, 10 years. That is actually inside the specification.
Okay.
In fact, so far, Prof. Chow on this topic, is one of my favorite questions, by the way. What I found was that, a lot of my students, when I ask them reclaim land, they have no idea. They have no idea a lot of our islands are reclaimed. You know why they got no idea? Because the engineers did such a good job. You're talking about the HDB engineers. You're talking about engineers who are the contractors. You're talking about engineers who are in the consultant. They did such a good job that the public cannot tell the difference between the two pieces of land. So engineering is at its best when it's invisible. When we are visible, then we're in trouble because things fail. So being invisible is good. So when we deliver that piece of land, it's supposed to behave like a normal land. It will settle. Right. Normal land will settle, but it can be tolerated by our standard designs in building the right foundations. So a very interesting side remark I thought I'll share with you.
Great. Any questions from the floor?
May I make a comment?
Yes, please.
Yes, Prof. Lee.
Prof. Lee, yeah.
No, the word skyscraper. You see, whether you have reclaimed land or natural land, if you talk about skyscraper, you still need reinforcing material like piling and so forth. You do not, even natural land, if you want to build a skyscraper, it's a different field of geotechnical engineering. You cannot reclaim land to build skyscraper.
So you need to have the piling right down to the bottom of the sea.
It's like any other natural piece of land with skyscraper, you have to do a pile, and the strength of the pile depends on how big, what type of pile, and how deep you have to go depending also the land way below your reclaim area, reclaim level. So that it must reach area so that your pile can develop the strength. So that economically you will recommend.
Thank you. Please identify yourself.
Yes, I'm Eric Beng. When I look at these three, there's one thing in common, and they are basically each and every one of them is a response to population pressure to create a livable space. Am I right?
That's correct.
So if we still stick within that sphere, this issue of relieving population pressure, is it true that there's another way, which is to live on water? Because we saw the mega scale of work, energy, and time that's needed to reclaim land. So if we can create another area, also for the same purpose of relieving population pressure, namely to build structures on water. Isn't there something going on in the Netherlands? They're always ahead, when dealing with water. Do you have some information on that? I know it's not directly related to that, except
Right.
that,
I'm not entirely familiar if Netherlands is doing it, but I do know, for example, one of our colleagues in the department is looking at these big floating structures. Of course, some of this original work, I think, was actually done by the US Navy. They were trying to build some of these floating structures that could actually serve as a mobile naval base, but that was too challenging, I think. But now we are trying to do it, as you have said, to create a new living space. I do not know the legalities, what the law says about whether a floating space is a real space. I think there are some interesting questions here. So far, in terms of these two competing ideas, floating islands and real land, in Japan, the real land people has been winning. The Japanese government is not willing to build floating stuff. As I've said, I'm not a legal expert. I think there's a difference between a floating space and a real piece of land. So that there could be legalities in this particular, but technically it's not a problem, I think. All right. Oh, by the way, just to add, the people working on it are structural engineers. There's another group of specialization in civil engineering. I thought I advertised for them too.
Hi, I'm Wan Yu from I-Square. So I'm just curious, how, with current best practice, for example, in Singapore, what is the rough cost of fill material, dollar per cubic meter of fill material? Just like rough guess, doesn't have to be precise.
It's a very good question. It's just like asking the cost for sand. I think this is a trade secret if I'm not wrong.
Okay.
Oh,
what about maybe like Watabe, if their information is public? Or?
No, you cannot find this information in the public domain. It's actually something that will decide whether you win the bid or not.
Oh, okay.
I do not know. As I said, the experts are sitting in front and they could correct me. And these are I think commercial secrets.
Oh, okay.
Yeah. But it's a good question, by the way.
You mentioned about slurry. Is there a cheap source of slurry?
Slurry usually comes about, especially when you are dredging as I've said, slurry for us usually comes about from the seabed, right? Because the seabed tends to be having this material, we call it the soft surface marine clay, SSMC. And this is actually the waste, I'm not allowed to use waste. Prof. Tan keeps saying that don't use waste, use unwanted soils. He knows what he's saying. All these unwanted soils are typically generated because we dredge the navigational channel. We need to maintain our navigational channels for the port. And when we dredge it, we need to put it somewhere. They are slurries.
Yeah, what about those that are deposited in river deltas, for example, they flow a lot of mud into the sea, right?
Right,
so
right.
Can
estuary.
As well?
Yes, estuaries. In fact, that is the material that was, the Haneda airport has this river. So they got a lot of soft stuff here, Tama River. So a lot of their clay that they used to reclaim this airport was from all this soft material.
So do we buy slurry from other places?
I think if we can carry any feel of any nature, we will try to carry sand. Yeah, it's interesting, by the way. This will not be part of geotechnical engineering. Probably the hydraulics engineers, Prof. Chan is an expert. Carrying all this sludgy material on big boats is a hydraulics problem. If Prof. Chan can crack this problem, he will solve another major problems for us. You see, civil engineers are very useful. I want to say that.
Okay, any more questions?
Hi, I'm a student from NUS High. I'd like to ask a question like, in land reclamation, do you see the possibility that one day we reclaim land to a point where our lands connect with the neighboring countries?
I can see that NUS High is training very bright students. Oh man, I don't quite know how to answer this. In fact, when I suggested this topic to my partners, my partners politely tell me not to talk about certain things. So this is like one of the out-of-bound topic I cannot talk about. Yes, Prof. Liu, yes, please.
The international laws, you can go all the way onto international boundary. So therefore, actually, in some of reclamations, we push all the way close to the boundary. So that the limit to our reclamation is actually the international boundary. No secret.
Yes, please.
Hi, I'm Abhilash from Mechanical Engineering. So when you use cement for land reclamation, is there any ecological impact of that? Or is there any studies regarding that, apart from using just the natural sand or slurry?
No, we haven't studied it. It's a good question, by the way. Something that perhaps we should be more sensitive. But I guess one of the reasons, I'm not saying this as an excuse, by the way. In Japan, this will be a major issue because they have a very powerful fishing lobby. And so, but the fact is that I've already cited all these existing case histories, and these are based in Japan. So my indirect reasoning is that it is not damaging the marine ecosystem. If not, this project will not fly in Japan. They are honestly, they are more environmentally friendly than us, no doubt about it. I've seen there are big projects where to reclaim land, for example, and not this piece of land. Another big island is Kangsa Airport. You all may have been there. It's totally artificial. And what I was told by the engineers is that before they reclaim this land, they actually send divers in to remove all the corals and all the wonderful sea flora and fauna. And then after they reclaim the land, they plant it right back. Very impressive, but very expensive too.
Just more curious, I read about the Pulau Semakau, the landfill area. Is that done in the same way using cement or just a natural one?
Oh no, it's being filled using incinerated waste.
But they create some boundary before filling, right?
Yeah. No, that is just the containment bunds. Those are using sandy fields.
Okay.
They are not using soil cement.
Yeah, okay, thank you.
But the inside of this inside of these compartments is our incinerator. That's the way we dispose of our solid waste. We burn it into ash, as Prof. Liu said. Yeah, so that reduces it to the minimum solid volume and we fill it up.
Thank you.
Actually, Pulau Semakau was built to dispose. Before Pulau Semakau, much of the waste were deposited our land surface here, and we don't have enough land surface. So we built Pulau Semakau by connecting a big island and with some small island, building a dike around it, so that the area inside happened to be quite deep, and we can fill it up with our waste instead of disposing in land here. And then I used to, when I was working there, I was half joking. I said, well, this is about 25 meter depth, So about 30 years, you go to the surface. They asked me what happened. I said, well, you can build another 30 years upward, And they said, what happened? You keep on building it up, I said, well, by that time you have to email me upstairs, I'm
As you can see, probably has the upper hand. By the way, the topic of discussion is this little island here. This is Pulau Semakau. Just for your information.
Okay, if there are no more questions, then we have to call this session to an end. Let's thank Professor Phoon again. Now call upon the Dean to present a token of appreciation to Professor Phoon.
Thank you very much.
So we've come to the end of the session, and thank all of you for coming. And do look into our website for future events. Thank you.
Thank you very much for coming.